Alright, we're starting chapter 5 now, moving right along. This chapter may have a little difficulty for some of you because it's not something you have done in probably all the math classes you've taken. Some teachers do it in high school and some don't as much. So I want to talk about this, try to talk you through it, and explain a little more than maybe the PowerPoint shows. Hopefully it will help, but be sure to ask questions or contact me if you need help with anything. Our topics or objectives are to talk about zeros of polynomials and solutions of polynomial equations and what exactly is a polynomial, graphing factored polynomials, solving polynomial inequalities, won't do as much with that, and finding zeros of polynomials. So let's get started. Alright, the number k is a zero of the polynomial function, and k can be a complex number. There are real zeros and there are complex zeros. We'll talk about complex zeros more later than we will this time. Okay. If pk is 0, if the function at that number is 0, because remember what that's saying is, if we have pk, we're really saying, if we have, excuse me, if we have this notation pk equals 0, that's really meaning that this is your x value, whatever it is, and 0 is the y value. So you have a point x0 that is a solution of your polynomial function. And if you graph it, of course, it will be graphed somewhere along this x-axis. So somewhere along here will be a k, and whatever value that is. And it can have more than one root. We can have 3, 4, and 5 roots depending on the degree of the polynomial, which we'll also talk about in a little bit. It's also expressed as a root or a solution. So these words that you see in red here on this slide are all words that depict the same thing. A zero, a root, or a solution is a point on the x-axis of a graph. It's an x-intercept of a polynomial if you were to graph it. So let's move on to the next slide. If we have a polynomial equation, and the variable x is then the x is your variable. And most of the time in math it is. It could be any letter, but we're going to say x is the variable. Where a to the n, a sub n means some coefficient a, and n is your highest power of x. And a sub n minus 1 is the coefficient that's in front of the next highest power of x. On down to where you have a sub 0, which is the constant. Okay? And the leading coefficient is not 0. And that's the degree. The degree of your polynomial is n. That's the highest power of x. So in other words, just to put this in an example, I always think with these definitions it helps to put it in an example. If I have, 5x to the 5th power plus 2x to the 4th power minus 3x to the 3rd power plus x squared, okay, plus 4x minus 10. You notice I've written this in descending powers of x. I started with x to the 5th, x to the 4th, x to the 3rd, x squared, x, and I'm also getting smaller in my writing, I noticed, but that wasn't intentional. Okay, so x to the 5th is the 5. This is a polynomial of degree 5. So the degree of this polynomial is 5, which is the highest power of x right here. So you always want to write it from highest to lowest power. And usually you want to have placeholders if it's missing a power. Say I was missing an x squared. I'd want to put a 0x squared there for kind of a placeholder. So in other words, if I was going to label this, 5 is my n, okay, and 4 is n minus 1, and 3 is n minus 2, okay, and then so on and so forth till I get to there might be 6 or 7 ... then n is 2 here, n is 1 here, and n is 0 at the constant. Okay, and then for our coefficients, if we're going back into that blue equation, 5 is our a sub n, 2 is our a sub n minus 1. It's the coefficient in front of that n minus 1 power. Then negative 3, or your negative 3 here, is your n minus 2. And then 1 is your coefficient in front of your x squared, where n is 2. 4 is your coefficient in front of your n1 term. And minus 10 is your last a sub 0. So this is a sub 0. Take this off. This negative 10 is a 0. Then this one is a 1. And the 1 is your a 2 ... Okay. And this is your a sub n minus 2. When I say sub, I mean subscript n minus 2. And that was your a n minus 1 and your a sub n. And so that goes with these. That's the coefficients. Those are your a's here. Okay, those would be your a's that go. There's a 1 there that we don't see. Okay. And so those are what we mean by the a's. And then the powers on the x's are your n's. And the degree is the highest power of x. 5 is your leading coefficient. It's also the degree, but you can also see that the highest power of x is 5 here, and your a sub n is also 5. It wasn't probably good to use that as an example and have the same number, but anyway. Okay, let's go to the next one. Verify that the given values of x solve the corresponding polynomial's equation. So you have 6x squared minus x cubed equals 12 plus 5x for x equals 4. And then you've got a complex solution in your next problem, and then x equals 0, and you actually have a complex number in the problem itself in problem C. So let's look at the answers to these. So we'll start with A. So it wants to know if x equals 4 is a solution. So for every x you put in the 4. And so 6 times 4 squared is 6 times 16 minus 4 cubed, which is 64. And is that equal to 12 plus 20? Well, if it is, then 4 is a solution. And it is. So it's a true statement. So 4 is a solution to the first problem A. And we just substituted the number in there to see if it worked and gave me, if it didn't come out the same, then it would not be a solution. Okay. So let's go on to B. And they want to know, this was a complex answer. 2 plus 2i squared and 2 times 1 plus 2i. I put that 1 plus 2i in for x. You notice the pink is what x was. Replacing the x's. And then minus 5. Now, the 1 plus 2i squared could give you some problems. So I want to go off on the side and just show you what that's going to be. I'm going to go up here at the top, right beside the original equation. 1 plus 2i squared is the same as 1 plus 2i times 1 plus 2i. And we double distribute our FOIL. So I have 1 times 1 is 1. 1 times 2i is plus 2i. Now I go to the 2i and distribute that, so I have another plus 2i. And then when I distribute 2i times 2i, I get plus 4i squared. And if you remember, we're going to combine like terms. So this is going to be 1 plus 4i plus an I squared. For every I squared, if you remember, we substitute a negative 1. Because I is the square root of negative 1, I squared is negative 1. And so then we've got, if we go up, we've got 1 plus 4i and minus 4. And so that's going to be, I can add these two together. So my final answer is negative 3 plus 4i. And that's going to be what we put under the 1 plus 2i squared. That's what 1 plus 2i squared would come out to be. And so this is going to go away when I take my annotation slide off, but you'll be able to rewind again and see it if you need to. Okay, so we got 1 plus 4i squared, which we already did. Distribute the 2 to the I plus 1 plus 2i, so that becomes 2 plus 4i minus 5. Okay, I have 1 plus 4i minus 4, which I already did up there. And 2 plus 4i minus 5. Combine the 1 and the negative 4 and the 2 and the negative 5. And I end up with negative 3 plus 4i equals negative 3 plus 4i. That's a true statement. They're exactly the same. So 1 plus 2i is a solution of x squared equals 2x minus 5. Okay, now let's look at this one. We have a complex number in our problem. What they're wanting to know if it's a solution or not is not a complex number. It was x equals 0. So we put 0 in for all the x's. Okay. 0 in the numerator we can do. And 0 over anything is 0. And 0 times anything is 0. So we get 0 equals 0. And that is a true statement. So 0 is a solution of this polynomial equation as well. So when you're trying to find the solutions, you just plug those, whatever it says, is this a solution to the equation, plug that number in, solve your equation, and if it comes out one side equals the other and they're exactly the same, then it's a solution. If they're not, then it's not a solution. All right, now this is end behavior of polynomials as x approaches positive infinity or negative infinity. And this is a lot of words, but hopefully we can make this make a little more sense. Given polynomial function p of x with a degree n, the behavior of p of x as x approaches, that's what the arrow means, x approaches positive infinity or negative infinity, can be determined from the leading term using the table below. And what we're really looking at is that you're really looking right now at a positive leading coefficient and whether the highest degree, the degree of the polynomial is even or odd. That, remember, degree is the highest power of x. Okay, and as x approaches infinity, what that means is when you have a graph, I don't know a good place to put it because this is a pretty full slide, but I'll put it up here. On the left, this would be as x is approaching negative infinity. So I've got my graph, okay, and I'm looking at the x's as they go this way. X is going to the left as x is approaching negative infinity. So as my x's are getting smaller, what happens to the end behavior of the graph? For x approaching positive infinity, I'm going to put that on the other side. For x is approaching positive infinity, as you would think, it says the graph is going this way, or as our x's are getting more and more positive, and our x's are getting higher and higher and higher. What happens to the end behavior of the graph? Okay. If n is even, so that means that the highest power of x is 2, 4, 6, 8, or something even higher. So this means as my x values approach infinity, right here, we're talking about as x approaches infinity, okay, this means what's happening to the y value? What's happening to the y value? Well, that means it's approaching positive infinity. So this is for all graphs okay, when n is even, that's the highest power of x is even, it's going to go up on the right and up on the left. Up on both sides is the end behavior. Okay? When n is even, x squared, x to the 4th, x to the 6th, x to the 8th, any of those things are going to go, if a is positive, that's the other caveat here. We're looking at this, that a is positive, okay? A is positive, that means it's any number. It can be any number, but it has to be positive. It can't be negative. It's going to go up on the right and up on the left. When n is odd, and again, a is positive, okay? If you read that first line, as x approaches negative infinity, it gets smaller, then your y, again, this is your y, approaches negative infinity. So that means it's going down here, and as it goes to positive, as x approaches positive infinity, y approaches infinity. So if your highest power of x is odd, it's going to go down on the left and up on the right as its end behavior. So you have x to the 3rd, x to the 1st, x to the 3rd, x to the 5th, x to the 7th, when you have a positive a in front. Okay, so kind of remember this. And we'll go to the next slide because it talks about more end behavior again, only it has a little different condition. Okay, so this is just a drawing of what I was saying. When n is even, and a is positive, the number in front is positive, it goes up on both sides. If n is odd, then it goes down on the left and up on the right. Now what happens in the middle varies depending on how big your polynomial is and how many bumps and curves it can have, turning points it can have. And sometimes there's several turning points. But we at least know the end behavior, which is, if it's even, it's up, or it's up on both sides. Odd, it's down on the left, up on the right. All right, so the next slide. When a is negative, the number in front is negative. Well, remember from when we did translations, if we have a negative in front, that flips the graph over, the x-axis. And so what's going to happen is going to make sense, because if we have this condition that a is negative now, okay, as a approaches negative infinity, y approaches negative infinity, so it goes down on the left, and as x approaches positive infinity, y approaches negative infinity, so it goes down on the right. So instead of, when a, the number in front is negative, instead of opening up, our graph opens down. It's flipped over the x-axis. Again, what happens in the middle depends on the polynomial. Now, think about what it did before when a was positive and we had an odd n. It went down on the left, up on the right. But now, as x approaches negative infinity, as x goes to the left, y goes to positive infinity, and as x goes to the right, y goes to negative infinity. So it's flipped over from what it was with a when a was positive. The graph rises to the left and falls to the right. And we'll see a picture of that, I'm sure, on the next slide. Okay, so you can see it's flipped over, a reflection over the x-axis when a is negative. So this says, sketch the graphs of the following polynomial functions, paying particular attention to the x-intercepts, the y-intercept, and the behavior as x approaches infinity. So we have negative x times 2x plus 1 times x plus 2. When it's factored like this, it's telling, you can tell the x-intercepts immediately. When it's in the form of b, x squared plus 2x minus 3, we have to factor it. And c, the same thing, we have to factor it. All right, so let's look at a. We're using the zero factor property. So we have a negative x, 2x plus 1, and x minus 2. So that means our zeros we find by setting each one equal to 0. So in case you forgot what you do there, That means that our x is equal to 0, that x by itself. Then we have 2x plus 1 equals 0, which is where we get the x equals negative 1/2. Okay, and then we have x minus 2 equals 0, which is where we get the x equals 2. So anytime you have a lonely x out there by itself, there could be a negative in front of it or a number in front of it, that value for the x-intercept is still 0. Okay, so we found our x-intercepts. Okay, and we list them as points. Remember, the x has a value. The y is always 0 where it crosses the x-axis. If we want to find the y-intercept, we could plug it in, put an x equals 0 and find it, but since we found the origin was an x-intercept, then that's also a y-intercept. So now let's look at the end behavior. What is the highest power of x? Well, look at our x's. Let's multiply. We have negative x times 2x times x. That's going to be negative 2x cubed. It's going to be our first. If we multiply these first numbers here, 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 and here, that would be our first term. And so negative x times 2x times 2x times x is going to equal negative 2x cubed. And so that would be our leading term. Our leading coefficient is negative, and our highest power of x is cubed, so it's odd. It's an odd degree with a negative coefficient. So now let's think about the end behavior. Okay, we have negative 2x cubed. The leading coefficient is negative and degree is odd. So that means as x approaches infinity, we're going to go, since it's odd and it's negative, excuse me, go back. Our basic formula is going to be up on the right and down on the left, since we have an odd leading coefficient, a negative leading coefficient and an odd degree. So let's look at their graph. Putting it all together, we get this graph. It goes, we have our three intercepts marked, negative 1/2, 0, and 2. And it goes up on the left and down on the right. And you could plot some other points in here in the middle to try to figure out how high this goes. We'll also talk about how to get some relative maxima and minima probably at some point. But you could plot a point there and figure out, about where these things are going to hit and get an idea. But mostly what we're going to want is a rough sketch for these graphs. Okay. Now let's look at the b. It's not factored, like I said earlier, so we have to factor it. Okay. We've got our last coefficient is negative 3. Our leading term is 1. So the y-intercept is our last coefficient, 0, negative 3. That's important to know, that if I put a 0 in for all the x's, all that would be left with the negative 3. So this is our y-intercept right here. And if we factor it, I'm going to go ahead and do it. I'm sure they'll do it on the slide. We have x and x. Our last number is negative 3, so that means I've got a plus and a minus in the factors, because that's the only way I'll multiply to be negative 3. Now, factors of 3, there's only 3 times 1 to get 3, and I need them to add to be a positive 2, so I'm going to say that it's plus 3 and minus 1. That will, when I multiply it, I get negative 3, and when I add them, I get positive 2. So that's how it would factor. Then we're going to use the zero factor property and set this equals 0 and solve it, and this equals 0 and solve it. So x equals negative 3 and x equals 1. And those will all be our x-intercepts. So we have 3 points. We have our y-intercept and our 2 x-intercepts. Okay. So we've done that. We've done it already, but that's what they found, which is what we found. And so we know our y-intercept is at negative 3, 0. So that could have gone on there as well. We know that the vertex of a parabola, which this is halfway between the roots. So you can kind of know that your low point is going to be halfway between -3 and 1, which then is at -1. So our low point is here. You could also calculate that value you wanted to. We had -3, 0 as a y-intercept. So that's 5 points you can have on your graph without any, without too much trouble. Just put your -1 in for your x's to figure out what your y value is for that vertex point. Or you could do the -b over 2a that we learned back in the preceding chapter. Okay. So now we're going to go to x to the 4th minus 1. Our leading coefficient is 1. Our last coefficient is -1. If I want to find the y-intercept, I put a 0 in for the x. So I'm just going to talk about that because I didn't really talk about it before. For your y-intercept, x is always equal to 0. So if I have y equals x to the 4th minus 1, and I put a 0 to the 4th minus 1, put 0 in for the x, then we know that y is equal to -1. I can always just look at the last number, the one without the x, and that's where it's going to cross the y-axis. So 0, -1 is our y-intercept. It's an even coefficient, so we know our end behavior is going to be, and it's a positive a, so it's going to be up and up. Okay. We need to factor and find our y-intercept, or x-intercepts. So x to the 4th minus 1 is a difference of squares. And hopefully you remember that would be x squared minus 1 and x squared plus 1. Okay? This is also a difference of squares here. So that's going to be x minus 1 and x plus 1. And then x squared plus 1. Okay? Now, this will not give us a real number answer. That's going to give us a complex number answer. These two, when I set them equal to 0, will give us x equals 1 and x equals -1 for our roots or our solutions, for our real number roots or solutions. So let's go on now. We've talked about, we've got 3 points. We've got 2 x-intercepts and a y-intercept. And let's look at our graph. And we know our end behavior is up on both sides. So we're going to factor, and then factored both our difference of squares. We did this already. And so here we go. And notice it's the x to the 4th. The higher the power, the even power, the more it kind of flattens out here in the middle. It doesn't have the nice kind of vertex that we have on our x squared. The x to the 4th, x to 6 would flatten out more. And so those highest power, even powers, tend to get a little flatter there at the vertex point. Okay. So inequalities is can be written in this form. It says solve the following polynomial inequalities. These are all factored, so that's nice. Okay. And we have x plus 3, x plus 1, x minus 2. A is less than 0. B is greater than or equal to 0. Okay. So the blue, notice our x-intercepts for both these are the same equation. So our x-intercepts are at -3, -1, and 2. Okay, and where is that? And we put our inequalities, or put our x-intercepts on the graph. We could find our y-intercept if we wanted to graph it by saying x equals 0. So we could have y equals 0 plus 3, 0 plus 1 times 0 minus 2, which is going to be 3 times 1 times negative 2. So y-intercept should be at negative 6. And we can see 1, 2, 3, 4, 5, that it is at negative 6 right there. Okay, so that kind of gives us some good points on our graph. Where is it less than 0, and where is it greater than or equal to 0? That's what we're looking for in an inequality. So we've got the red line. The red is less than 0. The blue is greater than or equal to 0, and it includes the points. The points on the x-axis are included with the greater than or equal to blue line. Okay. So from the graph we see that it's less than 0 on the intervals from negative infinity to negative 3. Okay, so from negative infinity to negative 3 is the red. Okay, so let's write this in red, if we're going to write it as an interval, to show how you would write that. Where it's less than is from negative infinity to negative 3 union, and it doesn't include negative 3, so it's the curved bracket there. Then it goes from negative 1 to positive 2, where it's below 0. And then after that, it's not below 0, so we can take that off. Okay. So that's where it is below 0. It's greater than or equal to 0. We're going to need to switch to the blue. Okay, and it includes negative 3, so we have a square bracket from negative 3 to negative 1. Hope it includes the negative 1. Oops, get my pen back. And union that with 2 to infinity, and infinity always has a curved bracket. So since it's greater than or equal to, the intercepts are included with the blue function. That's why we have the square brackets. And that's how you would you graph the inequality just like you graph it, and then you just determine where it's below the axis or above the axis for less than 0 or greater than 0. If it was another number, if say it was 2, you would have just marked it differently, but your cutoff point would have been, say, at 2 right here, and you would have made your domain choices or your value choices based on where it crossed that line instead of the x-axis. Okay. Okay, and we did these already. I had them color-coded, so hopefully they made a little more sense. Okay. You can also find the sign test method, and then pick numbers between, place zeros on the number line and put it into intervals. That's another way to tell. If it's positive, then it's above the x-axis. If it's negative, it's below the x-axis. And that you pick test points to do that. And so the way you would do that, if I want to solve this polynomial inequality, I have my zeros at 2, negative 5, and 4, and I want to know where it's less than or equal to 0. Okay? So we follow the steps in that procedure for the sign test. First we find the zeros. Again, positive 2, negative 5, and positive 4. Okay? And then we're going to put our zeros on a number line, which is kind of like putting them on the x-axis of a graph. And so the number line is split from negative infinity to negative 5. Then we have another gap from negative 5 to 2. There's an interval from 2 to 4 and from 4 to infinity. And we need to know which of these gaps or which of these intervals x is negative, or the answer is negative or below because it was less than 0. So we have our interval with test point negative 6. because if you notice, I'll go back, -6 would be out here, okay? So our -6 that we're going to test is in this interval. Then you're going to pick another number on this interval and another number in here and another number out here to test to see, and you're going to, if it's positive, it doesn't work. If it's negative, it's down here in relative to the y-axis. Okay. So we're doing our test point. They did -6, so you just put -6 in for all the x's and find out that it's -80. So our result was negative, and so it is negative from -infinity to -5. Then we go to our next interval, pick a number between those two. We're going to pick 0 because 0 is an always easy one to put in there. And we find out that it's positive, so it went back positive on the second interval between -5 and 2. Then we've got another interval to test from 2 to 4. So the integer between 2 and 4 is 3. So put that in there and find out that it goes negative again. And then after 4, somewhere between 4 to infinity, so pick 6. And we find out that it's positive again. So the two intervals where it was negative are the ones that we want. And so from -infinity to -5, union the interval from 2 to 4. Okay. Now, do we include the 5? Do we include the 2 and 4? You have to go back to the original inequality, which right here it says it includes the point less than or equal to 0. So you're including those 2 points, or the points -5, 2, and 4. If it was just a less than, then you would have curve brackets around everything because it wouldn't include the point that's on the axis. Okay, that's the end of this section. Hopefully that helped you. If not, please call and ask questions.